Today we're going to talk about partial sums and for geometric sequences and infinite series. So what we have here is our sigma notation, which indicates we're trying to find a sum from n equals 1 to 10. So for the first 10 terms of this sequence, which is geometric. It has a common ratio of 5/2, and implied here is start with 1. Now, the terms are all going to be pretty big, pretty quickly, and so the way that we do this, since you need a calculator anyway, is to use our calculator. So we're going to type in sum of a sequence, and then our 5/2 in a parenthesis, raised to the n minus 1 power in a parenthesis, and then comma n, starting from index term 1, ending with the 10th term. And again, when you use your calculator, it could be that you're using variable x here if you're in function mode. So let's actually type that up. So the second function of statistics is list, math item 5. Second function of statistic is list. Under ops is sequence. I need a parenthesis for my fraction. 5/2 raised to the, and I need a parenthesis for my power. X minus 1. Close that. And I need a comma, a variable, comma, index start at 1, comma, end at 10. Close, close. And our sum is approximately 6,357.162. I might take a swing at math fraction just to see if it will come up as a nice fraction, and the answer is no. So that is my sum. Let's try that again. This is the sum of the first 8 terms of the geometric sequence that starts with 5 and has a common ratio of -3/2. Again, I'm just going to let my calculator take care of this. Sum of a sequence, 5, open parenthesis, -3/2, raised to the x minus 1, close, comma, x, comma, from the first term through the 8th term. And it says my sum is about -49.258. Again, I'm going to try math fraction just to see if it's a pretty fraction. It is a pretty fraction. That's a preferable answer rather than a rounded answer. So -6,305 over 128. Definitely a calculator problem. Notice that the index has changed. It says start from the 0 term. The benefit of starting from the 0 term is that we can use just n rather than n minus 1 as a power. Again, I'm just going to let my calculator do the work anyway. Oops, go back. So clear that out. Sum of a sequence, 10, 2/3 in a parenthesis, raised to the, and now I don't need a parenthesis because it's just an x for my power. X is my variable. from the 0 term through the 50th term. Oops. Oh, it's thinking. So it's saying that it is 29.9999997. Again, I'm going to try math fraction just to see. Nope. If I round this, that 9 is going to force this to roll over. So I would say my answer is approximately 30. Okay. Let's go forward. This actually asks me to find the sum of all the terms, right? So this has now got a different different terminology. It's not called a partial sum because it isn't a partial sum. It's the sum of all the terms. So it's called an infinite series. An infinite series. And it's not always true that we can find the sum of all the terms, but if it is a geometric sequence, and so if it's geometric, and the absolute value of the common ratio is less than 1, meaning instead of growing, we're getting part of what we had before every time we go forward. So this sequence would start out with 2, and then you'd have 2/3 of 2, so 4/3, and then you would have 2/3 of that, so 8/9, and then you would have 2/3 of that, so 16/27, and then 2/3 of that, which would be 32/81. Notice that the terms are getting smaller and smaller. In other words, they're converging to 0. They'll never get there, but they will converge to 0. So if we're adding these, which we will be, then what's going to happen is we'll be adding smaller and smaller amounts. And believe it or not, we can then find the sum of all the terms. There's a formula for this. So if I have, I'm going all the way to infinity, and I have a geometric sequence with the absolute value of r less than 1, then my formula for finding the sum of all the terms is the first term divided by 1 minus the ratio. And the reason I call it the first term rather than a sub 1 is because in this case, the first term is going to be found by plugging a 0 in. And if this index had said from n equals 5 to infinity, the first term would be found by plugging a 5 in. Okay, so for this particular one, it's going to be, let's see, I'm going to plug in a 0. Anything to the 0 power is 1. So the first term of this will be a 2 divided by 1 minus, and the ratio is always the thing that's being raised to a power. So 1 minus 2/3. So that would be 2 divided by 1/3. 2 times 3 over 1. So that would be 6. And I can actually trick my calculator into finding that. So if I did, oops. Sum of a sequence, 2, 2/3 raised to the x from 0. And I don't have an infinity key. In statistics, I have an infinity key, but for this particular function, I do not have an infinity key. So I'm going to try something like 50. So my calculator says it's 5 with a bunch of 9s, so I would approximate it to 6 if it was a from 0 to 50. Then if I do second entry and I actually start bumping this thing up, let's do the first 60 terms. The calculator actually got fooled because there were enough 9s streaming across there to say that it is 6. But that's more of a tricky way to do it. Okay, so we have a geometric sequence. We are trying to find the sum of the terms all the way to infinity, so it is an infinite series. The common ratio is a number that is less than 1. So I can do, what would be the first term of this? Well, let's see, if the first term will come by plugging in that 0. So 0.2 to the 0 is 1. 4 times 1 is 4, divided by 1 minus 0.2. So 4 divided by 0.8. So 4 divided by 0.8. That would be 5. And if I tried to trick my calculator into doing it, because I maybe don't quite believe it, although tricking your calculator should not make you believe it more. Although sometimes we believe what we can see. 4 times 0.2 raised to the x, comma x, comma 0, comma, well, last time 60 worked, so let's try 60. Oops, what do I have? Oh, 0, comma, 60, close, close. Okay. It says 5. And what did I say? I said 5. Okay, let's try this again. It's an infinite series. It is a geometric sequence. The ratio is less than 1. So the first term is going to be found by plugging in a 4. So 125 times, let's see, 2, 4, 8, 16 over 5, 25, 125, 625. That's going to cancel and make 5. Okay, so the first term is 16 fifths divided by 1 minus 2 fifths. So 16 fifths divided by 3 fifths. So that's 16 fifths times 5 thirds. So 16 thirds, which would be 5 and 1/3, or 5.3 repeating. Alrighty. Okay, so we have 125, comma, nope, oops, open parenthesis, 2 divided by 5 raised to the x, comma, x, comma, from the fourth term through, I'm going to stick with 60, it's been good to me. And it's showing 5.3 repeating. If I said, well, maybe I think it's going to be something different, and I say, okay, the last couple times it actually kicked just a number, so I could go to 70. See what happens. It's staying the same. So it is 5.3 repeating. So that's infinite series for a geometric sequence. Okay.